So far, we've dealt with Lagrangians that have described a single particle that's able to move in x, y, and z. But if the Lagrangian method is going to have any power, it will need to be able to describe systems that are more complicated than that. And the purpose here is to show that that is actually not particularly difficult. So let's say that we have a system to begin with that consists of two particles. So there's one here at location R1, and one over there at location R2. So we can still identify a Lagrangian, which is the kinetic energy minus the potential energy. So just to be clear now, the Lagrangian depends both on the position of the first particle, the second particle, and their velocities, and in principle also on time. So this becomes then equal to the following here. First we have the velocities. And of course the square of a vector is a scalar, so that works out just fine. And then we subtract the potential. Now this is the potential. That could include both external forces and also two particle potentials, interaction potentials between the two particles. That's perfectly fine. Either way, we know, and we've shown earlier, that the force on the first particle is minus the gradient with respect to the position of the first particle of this potential. So that makes it not possible to write down Lagrange equations starting with Newton's second law, right? So Newton's second law here says that the force on the first particle in the x direction equals the time derivative of the first particle in the x direction, and same thing in the y direction. And then on we have f1x, f1y, f1z, and then we have f2x, f2y, and f2z, which is equal to P2z dot. All right. Now F1z, looking at this, it's going to be minus the derivative of u with respect to the x position of the first particle. So that's ddl, the x1, and that's going to be equal to the time derivative of the momentum here. So the momentum is going to be the L, the x1 dot. It's no different from before, because what we have in here specifically, r1 squared plus r2 squared. That's x1 squared plus y1 squared plus z1 squared, etc. So if I take the derivative with respect to, well, these are all dotted, of course, because these are velocities. So if I take the derivative with respect to any one velocity, I get the momentum in that direction because we're multiplying by 1/2 m in front. So this is true. And the same thing is true in the y direction. All the way down to the z direction of the second particle. So in other words, to describe the two particles that are not constrained in their motion anyway, we'll need a total of 6 Lagrange equations. And with this, Hamilton's principle is still valid. So the action, which is the integral of the Lagrangian, is stationary with respect to variations in any of the 6 variables on which the Lagrangian depends. That's what these 6 equations say. And as before, we can make any change of variables as long as we preserve the fact that each point in space is mapped by exactly one coordinate. So we can make a change of variables to generalized coordinates, such that we have Q1 through to Q6, where Qi will depend on, in principle, the position of both particles. So we can make up a coordinate system where a single coordinate depends on some part of the motion of two particles. That's perfectly okay, as long as we can apply this change of variable inside this integral here and get the same result. Then the action is still stationary in the same way, and that gives us then the same Lagrange equations. And there are still 6 of those. So there are 6 Lagrange equations for 2 particles. And by extension, if we have 3 particles, there will be 9 Lagrange equations. And if we have n particles, there will be 3n Lagrange equations. So the final result that we get here is that for a system of n unconstrained particles, we have 3n Lagrange equations. And the unconstrained part here is important. Okay. So that can be quite a few equations, of course, if we have a system with many particles. It turns out, though, that things are not quite so complicated, because if the motion of some of these particles are constrained in the sense that their motion is determined by the configuration of the other particles in some sense, then we can actually reduce the number of particles. And for that, we need to introduce the notion of degree of freedom. This has been a fairly short video, but since that is a very important topic, we're going to end this video here and deal with constraint systems at some length in the next video.